Greetings to you. Welcome to Physics Online class. I have been planning to upload videos of my experiments on my YouTube channel so that a good number of people that don't have access to experiments or good laboratories, as we do have in our school here, will be privileged to go through these experiments. One of the major reasons why people fail physics is that they don't have a sound knowledge in experiments. So, experimental aspect of physics was one of the major reasons why I created my YouTube channel. And I want to inform you that today, in this video, this is the first experimental video I'll be uploading on my channel. I would love you to share this video, share it and like my channel, subscribe to it, make your comments. I will all welcome all the wonderful, constructive and even destructive criticism so that we improve on my quality of videos and my services to you. Thank you. So in this experiment, I really want us to verify the principle of mixtures. You know, in physics, there are four main areas where we run experiments. We have mechanics, electricity, optics, and thermodynamics. So the experiment I'm running today is in the branch of physics called thermodynamics, that is heat energy. So we want to verify the principle of mixtures. In every experiment we want to run in physics, we always give a theoretical background of the experiment. So that is what I want to do right now. Let's start. Physics experiment. And where will be the experiments? Heat energy. Verification of the principle. Sorry, I don't have a good handwriting, but I believe this is readable. Heat energy, verification of the principle of mixtures. The principle of mixtures. Yeah. Let's start. First things first. What do you mean by heat energy? Straight to the point. Heat energy is defined as the form of energy that flows from region of high to region of low temperature due to temperature difference. Meaning if the two systems are in what we call thermal equilibrium, heat energy will not flow. So one system must be at a high temperature and then the other system at a low temperature. Hence, heat will flow. So this topic is a topic in physics we call measurement of heat energy. The first one is measurement of temperature and its units. Temperature and its measurements. So in defining heat energy, we talk about temperature. So what is temperature? Temperature is defined as the degree of hotness or coldness of a body. So in this experiment, we are concentrating on measurement of heat energy. So we'll be looking at things like specific heat capacity or thermal capacity. We will not touch latent heat of fusion or specific latent heat of fusion or vaporization. We'll concentrate on specific heat capacity and thermal capacity and all the equations therein. So what is specific heat capacity? The specific heat capacity of a substance or a body is defined as the quantity of heat energy that is required to raise the temperature of a unit mass of a body by 1 Kelvin or 1 degree Celsius. So in defining the quantity, specific heat capacity, the unit mass is an operational term that must be involved in that definition. I say it again for more emphasis. The specific heat capacity of a substance is defined as the quantity of heat energy that is required to raise the temperature of a unit mass of a body by 1 Kelvin or 1 degree Celsius. Mathematically, we have H is equals to mc d theta. Call this equation number 1, where N is the heat energy in joules, M is the mass of the body in kilogram, C is the specific heat capacity of the body or the substance in question in joule per kilogram per Kelvin. Joule per kilogram per Kelvin. And change in theta is a rise in temperature, that is theta 2 minus theta 1. Rise in temperature of the system due to addition of heat energy, or decrease in temperature of the system due to removal of heat energy. And so the unit is degrees Celsius or Kelvin or Fahrenheit. In Nigeria here we make use of degrees Celsius and Kelvin. So there's what I call the physics of cut and join. I'd love to clean this. The physics of cut and join. You know that from this equation, this quantity is called mass, the mass of the body. And we are dealing with water, heat energy, volume of water in this experiment. So recall that the density of the substance, rho, is equal to the mass of the body all over the volume. So if we make the mass of the body the solid formula here, you are having mass is equal to density times volume. You can call this equation 2, or let's say equation star. You can call this equation star. Now, we are going to substitute this quantity, that is equation star, into equation 1. We'll replace N with rho times volume. So we have H is equals to rho times volume times specific capacity times change in temperature. That is to say, H is equals to rho Vc change in theta. You can call this your equation number 2. Now, this equation number 2 is an equation we may likely use also in this experiment. What is the meaning of this equation? The first one here. Increase, that is the heat energy and the change in temperature, they are directly related to each other. Meaning, increase in heat energy into a system will cause the temperature of the system to rise and vice versa. However, M and C are constants. The mass of the body is a constant, and then C is a constant for a particular material or a particular body. So the next thing I want us to look at right now is thermal capacity. This everything we just discussed here is you can call it specific heat capacity. Specific heat capacity of a substance. So I would love to clean this so that we'll have more space and discuss thermal capacity. I believe you are there with your pen and paper writing. So don't forget that this video is all about experiments. But first things first, we must look into the theory behind the experiment. You need this knowledge because in every experiment, you must be asked to define something, to state a law. They may ask you to state the principle of mixtures. They may also ask you to do what? To define something. They may ask you to calculate, and you need all these equations. So please take notes. So we will be looking at thermal capacity. Thermal capacity. Thermal capacity, also known as what? Thermal capacity, also known as what? Heat capacity. Thermal capacity or heat capacity with a subscript CP. What is thermal capacity? The thermal capacity of a substance or a body is defined as the quantity of heat energy that is required to raise the temperature of the entire body by 1 Kelvin or 1 degree Celsius. Let me analogize this way. If I am the whole body, the quantity of heat energy that is required to raise my entire body temperature, we call it thermal capacity. Now, that is the entire quantity, the quantity of heat that is required to raise the temperature of my entire body by 1 Kelvin or 1 degree Celsius is what we call thermal capacity. However, for specific heat capacity, small c, the quantity of heat energy that is required to raise the temperature of my finger, this finger can be referred to as a unit part of my body, is what we call specific heat capacity. The quantity of heat energy that is required to raise the temperature of my finger by 1 Kelvin or 1 degree Celsius. I believe this analogy explains it better. So, for thermal capacity, mathematically, from H is equals to MC change in theta, we can say that this H is equals to what? Cp the theta. So H is equals to Cp the theta. This Cp stands for thermal capacity. We can call this equation. The last equation was equation 3, right? Sorry, I may write it wrong. Equation 4 now. Equation 4. So there's what I call the physics of cut and join. I'm sorry you can't find these statements in any textbook. The physics of cut and join, I mean this is it. Where you are able to create more complex equations using simple basic equations. So what are the conditions for doing that? So I call it the condition for creating this equation. Number 1, the two equations must have the same SI units for you to equate them with each other. And then the two equations must be used in the same condition, in the same scenario. You are free to do that. Do you understand what I mean? Okay, now, H is in joules. This H is also in joules. So we are free to say that this, which was equation 1, can be written as H is equals to MC change in theta, and this is also equals to what? Cp change in theta. You can call this equation star. Now if you look, we are free to say this is equals to this is equals to this, and this is equals to this. So we can write that MC change in theta is equals to Cp change in theta. Theta will cancel out theta. So you have your MC is equals to what? Cp. So we can say that Cp is equals to what? MC. This is equation number 5. So the specific, you can go ahead to make Cp the subject of the formula by saying Cp is equals to H divided by C is equal to H divided by what? Change in theta. So this is an equation for thermal capacity. And this is also another equation for thermal capacity. So for this equation, what is the SI unit for thermal capacity? H is in joules and this is in degrees Celsius. So the SI unit for thermal capacity is joule per degree Celsius. While the SI unit for specific heat capacity is what? That is C. The SI unit is what? Joule per kilogram per Kelvin. While for thermal capacity, the unit is what? Joule per degree Celsius or joule per Kelvin. Why am I emphasizing this SI unit? I've been marking Y for long now. A good number of students will solve it correctly, but then leave their answers without an SI unit. In physics, the SI unit tells us the quantity with which you are working with. If I just write 20 is just a figure. It does not make sense. But if I write 20 joules, somebody will know that I'm talking about energy here. So thank you. So right now, we are done with the theory and the mathematics of this experiment. These are the basic things you need to know. The next thing I want us to do right now is to look at the principle of mixtures. What do we mean by the principle of mixtures? What do we mean by the principle of mixtures? The principle of mixtures. The principle of mixtures states as follows. Heat gained by a substance. Heat gained by a substance from theta to theta 2 is equal to heat lost by a hot substance from theta to theta 2 is equal to heat gained by a cold substance from theta 1 to theta 2. In short words and in simple terms, the principle of mixture states that heat lost by a hot substance is equal to heat gain by a cold substance. Are you with me? That is the principle of mixtures. And with this, we are free to go. Now, for the principle of mixtures, we don't employ there are two basic ways to determine the specific heat capacity of a substance. One method is the method of mixtures, and the other one is what? Electrical method. For the electrical method, this is the equation you use, and we may need this equation in this experiment because WAEC, those guys are dangerous. I'm sorry to use these words. They can test your area, your level of understanding in almost all areas in a particular experiment. So WAEC, I'm very sorry. I'm not saying you guys are dangerous, but I'm saying you guys are wonderful. Thank you. So right now, we can say that from heat energy is equal to mc change in theta. Recall that in your current electricity, when electric charges are flowing through a conducting material, it gets to a point where they start heating up that particular material. And the quantity of heat energy generated when a potential difference is passed through a conducting material is given as H is equal to what? IVT. You know, from V is equal to IR. You can reproduce more equations here. This factor IV is called the power, while IVT is the quantity of heat energy. So we can say that P is equal to what? IV. In what? In watts. And this in what? In joules. So if this is equal to this, and this is equal to this, we are free to say that MC change in theta is equal to what? IVT. This is another equation, and trust me, we are going to make use of this equation in this experiment. So the next thing I want us to look at is the principle of measures is employed when we use a calorimeter. But in this experiment, we are not going to use a calorimeter because the volume of water that we're going to be measuring will not contain the calorimeter. The calorimeter cannot contain the volume of water we are going to make use of in this experiment. So for that reason, we make use of a beaker. So the next thing you see on this slide is the experiment guide. The experiment guide for this particular experiment we are running today. So I will quickly project and we'll look at the experiment, the instruction, and then you see the way I'm sweating. Let me take some water to calm down my temperature. Do you love to have? Okay. A minute, the PowerPoint is on. So look at the board quickly. Welcome to Physics Practical. The title for the experiment is Verification of the Principle of Mixtures. Aim to determine the thermal capacity of a substance. To determine the thermal capacity of a substance. So that is the setup for the experiment. We are going to heat this metal on this flame of fire, actually the Bunsen burner, and then the metal will gain some quantity of heat energy, and then we transfer this metal into this place. What we do for first things first is that we're going to measure the initial temperature of this system, record it somewhere, transfer this guy to this place, record the final temperature. We're going to be varying the volume of water in this experiment. So let's go. You are provided with a beaker, a thermometer, a stirrer, a measuring cylinder, wire gauge, Bunsen burner, a wire gauge, a 50 gram mass, a pair of tongue, water triple stand, and other necessary materials. Using this, the measuring cylinder, measure that of water, 150 cm³ of water into the beaker, record the volume V of the water in the beaker, calculate the mass M of the water, given that M is equal to rho times V. We did that during the theory. I hope you saw this in. Measure and record the initial temperature, theta naught of the water in the beaker. Hold the 50 gram mass with the pair of tongues in the flame of the Bunsen burner for 2 minutes. Underline 2 minutes. So quickly transfer the 50 gram mass water into the beaker. Stir gently and record the highest temperature θ1 attained. Evaluate theta T is equal to θ1 minus θ2. This is actually change in temperature, which we did during the explanation of the theory. Empty the contents of the beaker and repeat the procedures above for other values of V, because it's 200 cm³, 250 cm³, 300 cm³, and 350 cm³ respectively. Tabulate your readings. Plot a graph of M on the vertical axis and theta on the horizontal axis. Determine the slope S of the graph. Evaluate K is equal to 50 all over S. State 2 precautions taken to ensure accurate results. Define thermal capacity. I told you this, that in every experiment, you'll be faced with a particular theory where you will have to define something or state a principle or whatever. So in this case, I ask you to define heat capacity. So that is the calculation. An electrical kettle rated 1.2 watts is used to heat 800 grams of water initially at a temperature of 20 degrees Celsius. Neglecting heat losses, calculate the time taken for the kettle to heat the water to its boiling point. Take boiling point of water to equals to 101 degrees Celsius. Specific heat capacity of water, C subscript W is equals to 4,200 joule per kilogram per Kelvin. So this is the experiment. The next thing I want us to look at right now is to quickly generate the table of values. And I will teach you how to do that. Generate the table of values for this experiment. Okay. The table of values is something I need to pause a little bit and talk about it. It carries the bulk of the marks in physics experiments. I want you to know that if you can do your experiment very, very, very well and get it 50 over 50, and you also do your theory and OBJ, that is paper 1 and 2 very well, there's no way you cannot get an A1 in physics. Please follow my videos and share them out. I have particular interest in physics experiments because that is where the strength in making A1 lies. So don't joke with your table of values. Don't joke with your table of values. For this particular experiment, watch how I will generate it. Go back to the instruction. I'll read from here. So we write as observations slash table of values. We start with serial number. You draw this line. Now, we are going to pick up the parameters in the experiment. One of the parameters in the experiment is volume. Volume is measured in cm cubed or meters cubed. But in this experiment, we are making use of cm cubed, not meters cubed. So write volume slash cm cubed. Draw this line. The second parameter in this experiment is calculate the mass m of the water, given that mass m is density times volume. So we have mass as another parameter. Sorry, that is the bell from our school. I'm sorry about that. Sorry for the interruption. So mass is given as what? Density times volume. And the unit of mass is what? Grams. We are not dealing with kilogram here for now. You draw your line. The next parameter is theta naught. Theta naught is measured in degrees Celsius. You write it down. Theta naught in degrees Celsius. You write it down. The next parameter is theta 1, measured in degrees Celsius. You write it down. The last parameter is theta 1 minus theta naught, all in degrees Celsius. We call this the composite table. If you don't record your composite table very well, you will lose marks here. I won't explain the details of the marks we lose. Let's concentrate. So you are to run this experiment. The first value is 150. Write it, record it to at least 2 decimal places. Don't ever record it as 150. You must record to at least 1 dp. But I always tell my students, record this to at least 2 dp. I will quickly say something here. For all these values, we are going to record all of them to 2 dp. But in the case where you have values like maybe V inverse, maybe root V, maybe log V, or V to the power of 2, in this case, you will record to at least 3 decimal places. If you have anything like this in your composite table, then you have to record everything to 3 decimal places. Inverse, root, log, square of number, or V cube, whatever the case may be. You must record to what 3 decimal places. For in this case, we don't have anything like this, so we record at least to 1 dp, but we will record here to 2 decimal places. So 150.00. That's a record is. The second value was what? The second value was 200. So we write 200.00. The other value is 250. 250.00. The next value is 300. 300.00. The other value is what? 350. Right? 350.00. So you draw a line this way. You draw a line this way. This way. This way. Looking at this table of values, we are to perform this experiment. We are to run this experiment for like 1, 2, 300.00 and this. So I'll quickly explain how I got this. This value is mass is density times volume. So every value here is the volume, and density is 1. So every value here times 1 will give you this value. As I told us initially, we have to record to 2 decimal places. I want to talk about something quickly before I move down. If I come and record 300.0, we call it inconsistency. I don't think WAEC will allow you to write something like this. And that was the reason why I was saying those guys, they are dangerous. Not that they are dangerous, but they are very strict and standardized in their marking guide. So right now, the next video you will see right now will be a video on how this experiment will be run. I'll quickly go back there and have it in mind that the equation H is equal to mc change in theta, and that mass H is equal to density times volume times this change in temperature is a particular equation that contains all the variables in this experiment. Thank you for your time. God bless you. So for this experiment, these are the apparatus we need for this experiment. This is the stirrer, this is the beaker, this is the pair of tongue, and this is the mass. This is the mass we are going to hit on the flame of fire. We hold it this way, and this is the cylinder to measure the volume of water. The lighter that we use, the thermometer. This is a liquid in glass thermometer. The thermometric substance here is alcohol, and this is red alcohol. The calibration of this thermometer is from 0 degrees to 100 degrees Celsius, and then from 0 to minus 10 degrees Celsius. So the upper fixed point here is 100 degrees Celsius, and then the lower fixed point here is 0 degrees Celsius. It is calibrated to 1 degree Celsius, as you can see. So here is the Bunsen burner, and to expedite action in this experiment, I have already measured some volumes of water here so that we can use. I have 1, 2, 3, 4, 5 cups here in the ratio, in the order of 150, 200, 250, 300, and 350 cm cube of water. So right now, the first things first we're going to do is we will pour this water here and verify if this water is 150 cm cube. So if you bring this close, we need to add more volume of water here to make it 150 cm cube. So we're going to add more volume. Yes, the water is exactly 150 cm cube. We'll not stop there. We are going to pour the water here. Yes, we are done with that stage. If you can observe very well, this thermometer is at it has 30.5 degrees Celsius. If you look at it very well, it is on 30.5 degrees Celsius. So we are going to measure the initial temperature of the water. But before we do that, I'm going to transfer my table of values on the board down here. So I will write again. Serial number. I will draw a straight line down. This is 1, 2, 3, 4, 5 times of experiment. And then my V/cm cube. This is how you record your table of values in your external exams. Please take notes. And then your mass, which is equals to rho times volume. The units of this is grams/grams. You draw your line down. You have your theta naught / degrees Celsius. You draw your line down. You have your theta 1. And so we have our theta 1 minus theta naught / degrees Celsius. You draw it down. These are the first things first to do in your experiment. So we have 150.00. We have 200.00. We have 250.00. We have 300.00. We have 350.00. We have the same here. We still have 150.00. And so this is your table of values. Please take note. This is how your table of values must look in your WAEC or NECO or GCE or IGCSE exams. Thank you. So the next thing we're going to do is we'll measure the temperature of this water. The initial temperature of this water. If you can see from this thermometer, the initial temperature of this water is 20. This is 25, 26, 27, 28. 28 degrees Celsius. 28 degrees Celsius. So our theta naught is 28 degrees Celsius. So we'll record 28.00 degrees Celsius. Can you see that, please? That is it. So the next thing we are going to do is we will heat this. We heat this for 2 minutes. We heat this here for 2 minutes and then transfer it to this and then record the highest temperature.